Welcome to the 8th and final seminar of the Fik3505 Wireless Multiple Access Protocols course. In this seminar we're going to cover access protocols for multi-hop networks. Instead of textbook references, we have a number of journal articles that can be found on the website. So what are multi-hop networks? Well, in this particular figure we can see a tactical radio scenario where a number of military units are communicating in a situation where there is no existing communication infrastructure available. And a multi-hop network allows for communication beyond the radio range of the individual radios. And we're going to see that networks of this type need to self-organize, since we not know in advance exactly where the different mobile units will be. And the applications that we envisage are mainly technical networks and various sensor networks. So how does a multi-hop network operate? Well, in this particular example we have a number of nodes distributed over the surface, and the gray lines indicate possible communication links, wireless communication links. And for instance, if node A on the left-hand side wants to communicate with the node B on the right-hand side, this node can do it by letting intermediate nodes storing and forwarding this packet. So a packet traverses from, for instance, CCN1 to CCN2 and finally reaches B. Such a network is what we call a low hierarchical system, and it becomes fault tolerant, since if individual nodes fail, there may still be a different route that can take a packet from A to B. So what are the various research problems that we encounter when designing a multi-hop network? Of course, wireless access protocols is the one of the key problems, or the access management. How should the different nodes share the wireless communication channel? And the other issue is the mobility management issue. Which path should a packet take through the network as it hops over different nodes to reach the final destination? And one particular problem is, of course, in the mobile scenario, is the network still connected? Is there actually a connection between A and B, as in our previous examples, or is there a break somewhere? Is a critical node failing? For instance, if CCN2 in this example fails, there is no path from A to B. So the access management, mobility management are the key issues. So how can these networks be modeled to allow for analysis of the performance? First, we look at the modeling of the positions of the nodes, and typically random models are used. We could use square grids, but mainly the most popular model that is used are two-dimensional Poisson processes. Also, the mobility can be an issue. How do the different nodes move? Typical models here are Brownian motion type mobility models, or structured models when you, for instance, model a battalion of tanks or something like that moving in a certain direction. The other issue is how the propagation and interference and collisions are modeled. Let's assume that we have as in the graph here, there's a packet emanating from node K that wants to reach node L. And in some intermediate point I, we transmit the packet from node I to reach node J. And there are a number of possibilities how we model the interference and potential collisions at node J. A very popular model is to consider the interference range. So let's assume that within this circle, if there is a transmission from any other node within this circle, we can assume that the transmission is collided. So this is a very simple model for collisions. A more complex model is then if you look at the individual stations, we make a interference graph to complement the possible wanted transmission. We can also have a graph that shows which nodes can potentially interfere with node J. And finally, the most detailed model is to compute the signal to interference ratio, to actually compute the path losses from both interferers and wanted signals here, like in the equation at the bottom of the slide, showing the wanted signal from transmitter I, and then we compare it with the noise and the interference from other transmitting nodes. And if the signal to noise or signal to noise plus interference ratio is higher than a certain value, then we say that transmission is successful. Otherwise, the message is lost, either due to noise or to a collision. So let's look at the other issue, and that is the traffic modeling. Typically, the traffic is modeled as Poisson arriving packets, and we also describe how the traffic is distributed in the network by the traffic matrix, capital lambda, where each element lambda ij represents the number of packets per time unit that are generated in node I and are destined for node J. And of course, the simplest case is when we have uniform traffic, that all the lambda ki are the same. The performance can in the usual way be computed by looking at the individual pairs, looking at the expected delay from K to L, and then we can also look at the average delay when averaging over all source destination pairs. There are, of course, distinct advantages with a multi-hop network, as it extends the range of the individual nodes, so we can get a much better coverage. But what is the drawback of multi-hop networking? Well, in 2000, Gupta and Kumar posed this question: what happens if we have a number of nodes in a given area, and each of them is transmitting with a fixed bit rate, and there's a fixed transmission range? What is the capacity that each node can achieve, or what is the maximum packet arrival rate to every node in order to have a stable system? Well, they found this following interesting result, that the traffic load per node as function of n tends to 0 as 1 over the square root of n as the number of nodes increases. So as the more nodes we have in a given area, the less is the capacity. So the multi-hop feature has this drawback that multi-hopping also consumes a lot of capacity from the various nodes. So this brings us to our first quiz, and as usually you have to pause the recording to figure out the correct answers, and when you have found the correct answers, then you can restart the recording. And here are the correct answers. The capacity per terminal in a wireless network does not increase with the number of terminals. In fact, Kumar and Gupta showed it decreases as the square root of n, where n is the number of terminals per area unit. Routing and channel access can be treated as separate in a multi-hop wireless network, and that is not true. They are tightly connected. It really matters in which direction we transmit the packet and where will our receiver be. The component ij in the traffic matrix indicates the expected number of packets that arrive at node I, which destination j per time unit, and that is correct. And multi-hop networks are indeed low hierarchy fault tolerant networks. So let's look at the access management problem, and as usually we go to our protocol classification, and let's start with the ALOHA protocols, or probabilistic dynamic resolution protocols, and see how they can be applied in a multi-hop setting. So let's look at a simple ALOHA type access scheme as we combine it with a routing algorithm. Let's assume that we have a random network, and we have, without loss of generality, we can pick a certain node that has a packet in the origin O, and let's assume that that packet is to be transported towards a destination that is very far away. And our routing algorithm now picks a node within our radio range R, and in this case we denote this node A, and we note that the progress we made towards our destination zeta is sort of the projection of the link between O and A on the source destination line. And what we want to do is to find an access protocol and a routing protocol that maximizes the expected forward progress. That is the speed, the inverse of the speed at which the packet travels to the destination. And the expression below here, zeta, shows this expected forward progress that can be written as the probability that we have a successful transmission times the expectation of zeta, which is the expected progress. Yeah, we can pick a number of various routing algorithms. A very simple algorithm is the so-called hot potato algorithm, that we simply forward this to a random node in the vicinity. A more effective algorithm is the nearest with forward progress or the maximum forward within range algorithms. The nearest with forward progress has the advantage that since the transmission is a very short distance away from the origin, the probability that we'll have a good signal to interference ratio is very high. So the probability of having successful transmission will be high, but on the other hand, zeta is likely to be small. The maximum forwarded range is the opposite. We try to pick a destination as close as to the destination as possible. This means that the zeta will be large, but on the other hand, the probability of a successful transmission will be less, since the transmission distance is very large, so that our signal will be weak when received at the receiver. So let's illustrate how this works for a maximum forward within range algorithm. Here we have picked the node that is closest to the destination. And so this is the node that has the maximum zeta within the range R. And this means that the shaded area marked A here cannot contain any nodes. Otherwise, the node that we selected would not have been the maximum forward within range. So this is using this area and using the Poisson probability, we can compute the density function and the expectation of zeta. So then it remains to compute the success probability, and using the interference radius algorithm, we can say that if there is no transmission in the dotted area here, we have a successful transmission. So we can use the Poisson probability to determine the probability of no other transmission in this area. And by this we can compute the expected forward progress z. So this brings us to quiz 2. Here we study the nearest with forward progress routing scheme, and you're requested to show how you could derive an expression for the distribution function capital F of z for zeta for the forward progress. So use the approach in the previous slides to do this, and when you've can pause the recording at this point, and then you do the calculation, and when you've found the answer you can restart the recording. So here's the solution. We picked a node S using the nearest with forward progress, and this means that there cannot be any node with less forward progress than node S here. So there cannot be any node in this half circle indicated in the graph. And with that you can compute the probability that of the length of the path S, and that is simply that the probability that there is no other node in the half circle, and that is given by the Poisson probability distribution. It's a little bit more tricky to get the distribution of zeta here, since this is the projection on the destination line, and assuming that the angle between the destination and the routed node S is phi. We have to condition on phi, and phi is uniformly distributed between between minus pi over 2 and pi over 2, since this is a 2D Poisson process, and we have to take away the condition of on phi, and we get the integral expression below, which we can evaluate numerically. So let's go and have a look at the other possibility of doing access management, that is deterministic or conflict-free access management, and we use a technique called the spatial time division multiple access protocol. The simplest way to do a protocol that is conflict-free is to schedule the transmissions from the individual nodes separately. So we do what we call a transmitter schedule or a node schedule, which is simply basically TDMA. So in slot number 1 we enable node A, and in slot number 2 we enable node B, and so on until we have enabled all the 5 nodes in this example. So this is the simple node schedule. But we can be a little bit smarter here, and we can, instead of enabling the nodes, we can actually enable the various links. So we note that, for instance, that in our interference model here, that a transmission can occur between A and B, and because D and E are so far away from A and B, they can transmit at the same time. So we can simultaneously transmit between D and E. Between C and B we can transmit, but then C will interfere with D and E, so there cannot be any transmission at the same time, and neither can A transmit, since it's only B that can receive signals from A. So when C is transmitting, there will be a collision at B. So C and the link CB has to be single, and so on. We can go on. In this particular example, the possibilities of scheduling various links is not so rich, but we can get a link schedule like this. The node schedules are simple. They don't allow for frequency reuse or channel reuse, but on the other hand, they can get delay guarantees for the various nodes. Whereas link-oriented scheduling or a spatial TDMA scheme is a little bit more complex. It provides high capacity, throughput, and can also get delay guarantees, and And as we will see later, it can also allow for the combination of scheduling and adaptive antennas or directional antennas. So that brings us to quiz number 3. And for a simple network as above with the 4 nodes, you're requested to design a minimal node schedule and a minimal link schedule. Minimal means the shortest schedule that you can find where all links can be activated. And the interference situation is indicated by the circles around every node, and if a node is within the interference range of a other node, there may be a collision if they transmit simultaneously. And you're also asked to determine which of the schedules will be more efficient. And as usual, you pause the recording at this point, and when you're done and have figured out the answer, then you restart the recording. And here is the solution to the quiz. First, we can see that the node schedule is of course very simple. It enables the 4 nodes one at a time in each slot. So this gets you a 4-slot schedule. As we try to make a link schedule, we can see that there are 6 possible links, and you can see that the link A to B can share the same slot as D to C, as the gray circle around A and the gray circle around D do not intersect. The same goes for the reverse transmission, that B can transmit to A at the same time as C can transmit to D. Again, the interference, the blue interference circle around C doesn't affect A, and the red interference circle around B doesn't affect D. On the other hand, when B and C are transmitting, their interference circles both touch D and A, so they have to be alone in a slot. And here we can clearly see that we get a link schedule that is also 4 slots, but it allows for frequency reuse, so the link schedule in this case is more efficient. So far we've been dealing with very, very simple interference models. So what happens if we actually apply a signal to interference ratio based models? And work of this type has been done by Grönkvist in 2005, where he actually used a terrain simulation, an actual terrain, and placing random nodes in this terrain gives various network realizations, as in the figure on the right hand side. And for all these networks he generated randomly, he computed the node and link schedules that would apply, and he got results of this type. The left hand curve shows the relationship between the delays in the link schedule and the node schedule, or you can say the length of the link schedule compared to the length of the node schedule. And this is the delay for low traffic. If we have a long schedule, link schedules tend to get very long, and for a long schedule we have to wait potentially quite a long time until our particular slot for our particular link shows up. And as may be expected, the relationship between the delay in the link schedule and node schedule, which is on the left-hand axis as function of connectivity, looks like this. Connectivity 1 means that all nodes are connected, and low connectivity means that the network is very sparse. As we can typically see here, the more connected the network is, the more effective becomes the node schedule. As in a highly connected network, there's very little frequency reuse that we can exploit. On the other hand, the right-hand curve shows the maximum throughput, or the capacity, and here we can see that here we compare the maximum throughput for a link schedule divided by the maximum throughput for a node schedule, and we can see that the numbers are larger than 1, on the y-axis, showing that the link schedule is almost always more effective when it comes to maximum throughput. On the other hand, the relationship to the connectivity is somewhat more unclear, as the plot shows. So finally, look at some of other issues involved in schedule design. When the traffic in the different links is very different, we can employ traffic-sensitive schemes. In particular, in this graph, in our example here, if the traffic is uniform, if all nodes transmit packets to all the other nodes in a uniform manner, it's obvious that node C will be very heavily loaded. So a lot of traffic will go through links B to C and also to C to D or C to E. And this can be managed by estimating the traffic, and then we schedule multiple slots in those for those links that carry a lot of traffic. And but this particular schedule below here, we could either schedule C and E several times in the node schedule, or we can schedule the link C to B and C to E several times in a link schedule. Another problem is related to the schedule maintenance and has to do with the mobility. What happens if we have a mobile network and the different nodes move? And this example, node D moves closer to node B, and suddenly there is now interference from node B. Which means that the link E to D cannot be used at the same time as B to A, as station B will interfere with the station D's receiver. So there are several options that we can do. Of course, we can recalculate the schedule, or we can have a collision resolution algorithm involved. Or we can simply drop certain links from a schedule. Or we can have interference margins, making sure that the interference margins are high, which means that we can tolerate more interference than actually is needed. All these remedies, of course, will decrease the performance of the network. This figure finally shows the use of directional antennas. If we have a link-based schedule, we can use adaptive antennas to protect our transmissions even better. Here we have a number of nodes 1 to 8, and here we can see that the superimposed on the links, we can see the antenna patterns of the antennas. So if a station transmits towards its intended receiver, it will direct its energy toward that receiver, and very little interference will go to the surrounding nodes, which means that the different links can be protected from each other in a much better fashion, and frequency reuse or spatial reuse becomes much more efficient. And that brings us to the summary. Multi-hop networks allow for the extension of the range of a single node, and by using store and forwarding of packets. And this, of course, can provide a high reliability, and packets can be forwarded to the final destination as long as the network somehow stays connected. The drawback in multi-hop networks is that the channel access and the packet routing are closely connected. We can use conflict-free or contention-based scheme, and the drawback is that the capacity and delay characteristics of the network deteriorate rapidly as we extensively use the packet forwarding in the system.